Now, in this lecture, we'll answer on two questions. In the first question, we find out the area of this circle, and in the second question, we find out the area of this trapezoid ABCD. So we start with the first question. In the drawing, we have a circle. Also, this is the current standpoint point P. From this current standpoint point P, we have two tangents to this circle, tangent PA and tangent PB. In addition, we have also the right triangle ACP. This angle ACP equals to 90 degrees in size, and the right triangle ACP cuts the circle at 2 points, point A and this point. In addition, we know that side CP of this triangle ACP equals to 4 units in itself. This is line 7 BC, is equals to 1 unit. Again, our mission is to find out the area of this circle. So, here we can implement rule 2. I'll repeat quickly on rule 2. According to rule 2, the lengths of two tangents for a common standpoint to a circle are equal. So, in the drawing, we have a circle, and this is the current standpoint point P. From this current standpoint point P, we have two tangents to the circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. Why? Because in our drawing, this is the current standpoint point P. From this current standpoint point P, we have two tangents to the circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. So write it down. PA equals to PB according to rule 2. It is given us in the question that tangent PB, this is tangent PB, tangent PB equals in total to 4 plus 1, that is 5. So PB equals to 5. We can write that PB equals to 5. And from this equation, PA equals to PB equals to 5. We derive that PA is also equal to 5 units in its length. So here, PA equals to 5 units in its length. In the next step, I'll copy the right triangle ACP in a new page, and we will implement the Pythagoras theorem on this right triangle ACP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the version for Pythagoras theorem. So actually, this is the right triangle ACP, this is equal to the original drawing. According to the Pythagoras theorem, in this right triangle ACP, AP squared, that is the square of the hypotenuse, is equal to AC squared plus CP squared. So I write it down. AP squared equals to AC squared plus CP squared. AP is 5, therefore AP squared is 5 squared, that is 25. And it is equals to AC squared. AC is the missing side, so we will leave it as it is. Plus CP squared. CP is 4, therefore CP squared is 4 squared, that is 16. So in total, if we found out the 25 equals to AC squared plus 16. Here we subtract 16 from this equation. And we get that 25 minus 16 is 9, so 9 equals to AC squared. Here we take a root out of this equation and finally get that the missing side AC, the length of the missing side AC is equals to the square root of 9, that is 3, so AC equals to 3 units and it's 9. If we side AC, that is equals to 3 units in its length. Here AC equals to 3, I write it down here, that AC equals to 3 units in its length. In the next step, we define the center of this circle. This point is point O. We define the radius of this circle as X. In the next step, we join points O and B together by a straight line. What is the definition of line segment OB? Line segment OB starts from point O, that is the center of the circle, and then to point B, that is the point of the circle itself. So this is exactly the definition of a radius. Therefore, OB is the radius of this circle, that is equals to X according to our definition. So here we can implement rule 1. Perpendicular of rule 1, according to rule 1, a tangent to the circle is perpendicular to the radius, 1 to its point of tendency. So in the drawing, we have a circle, and we have also tangent AB. This is tangent AB. Tangent AB is tangent to this circle at point M. In addition, we have the radius OM that equals to R. The radius OM is on to point M, that is the point of tendency of tangent AB with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 1. So we can actually implement rule 1 in our drawing. Why? Because in our drawing, we have the radius OB that equals to X. The radius OB is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle is equal to 90 degrees according to rule 1. It is given us the question that PB is a tangent to this circle. So PB is a tangent, it is absolutely straight line. So if we focus on the upper side of this straight line PB at point C here, so here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So in our case, it means that the sum of the angles on the upper side of the straight line PB at point C must be equal to 180 degrees. So which angles we have at the upper side of the third line PB at point C? Here we have this angle that is right angles plus this missing angle. In total they must be equal to 180 degrees according to all three. Therefore this missing angle must be equal to 90 degrees in its size. In the next step we will do a construction. That is to say, from this point O, that is the center of the circle, we will draw perpendicular on AC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AC. This point is point E. By doing this construction, we can do quadrangle OECB. Inside quadrangle OECB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle. In total, the sum of those 4 angles must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrangle OECB, we have 4 right angles. And according to rule 5, any quadrangle that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrangle OECB as a rectangle because it has 4 right angles. So I write it down. This is quadrangle OECB, and according to rule 5, this quadrangle OECB is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle OECB, side BC must be equal to the opposite side OE. But BC is 1, therefore OE must be also equal to 1. Likewise, according to the same rule, in the same rectangle OECB, side OB must be equal to the opposite side EC. But OB is x, therefore EC must be also equal to x. What is the length of this missing line segment? Line segment AE. From the drawing, it is very easy to see that AE equals to AC minus CC. Again, AC minus CC equals to AE. So I write it down. AE equals to AC minus EC. So A equals to AC. AC is 3. AC is 3. Minus EC. EC is x. So in total, A equals to 3 minus x units in its length. A equals to 3 minus x. In the next step, we will join points O and A together by a straight line. OA is of course the radius of this circle that is equals to x. So in the next step, I'll copy the right triangle OAE in the new page and we'll implement the Pythagoras theorem on this right green triangle OAE. So here by PT is abbreviation for pedovastoren. Okay, this is the right green triangle OAE that are going through the original drawing according to the pedovastoren in this right triangle OAE. OA squared, that is the square of the hypotenuse, is equal to AE squared plus OE squared. So I write it down. OA squared, that is the square of the hypotenuse, is equal to AE squared plus OE squared. The hypotenuse OA is x, therefore OA squared is x squared, and it is equal to AE squared. AE is 3 minus x, therefore AE squared is 3 minus x squared, plus OE squared. OE is 1, therefore OE squared is 1 squared, that is 1. So in total we shall find out that x squared equals to 3 minus x squared plus 1. Here we'll open the brackets on this side of the equation, and we get that x squared equals to 3 minus x squared. 3 minus x squared equals to 3 squared, that is 9, plus x squared minus 2 times 3 times x, that is minus 6x, plus 1. So here we have x squared on both sides of the equation, so x squared will get cancelled. Also you cancel x squared, in this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have 9 plus 1, that is 10, minus 6x. So in total we should find out that 0 equals to 10 minus 6x. Here we add 6x to this equation, and we get that 6x equals to 10. So here we divide this equation by 2, and finally get that 6x over 2 is 3x, and it equals to 10 over 2 is 5, so 3x equals to 5. Here we divide this equation by 3, and finally get that x equals to 5 over 3 in its length. So if we found out that the radius x of this circle is equal to 5 over 3 in its length. Our mission is to find out the area of this circle. Actually, the area of any circle equals to pi times the radius of the circle squared. So, write it down. The area of any circle equals to pi times the radius of the circle squared. And therefore, the area of this circle must be equal to pi times the radius of this circle squared. The radius of this circle is x. Therefore, the radius squared is x squared. So in total, we found out that the area of the circle is equal to pi x squared. So it is pi times x squared. X is 5 over 3, therefore x squared must be equal to 5 over 3 squared. So in total, we found out the area of the circle is equal to pi times 5 over 3 squared. So it is actually pi times 5 over 3 squared. 5 over 3 squared equals to 5 squared, that is 25, over 3 squared, that is 9. So in total, we found out that the area of this circle is equal to either 25 pi over 9 square units, or in terms of numbers, the area of this circle is equal to 8.727 square units. 8.727 square units. And again, if we found out that the area of the circle is equal to either 25 pi over 9 square units, or in terms of numbers, the area of this circle is equal to 8.727 square units. So we'll finish with the first question. In the next step, I'll present to you the second question and we will solve it. In the second question, our mission is to find out the area of this trapezoid ABCD. It is given us the question that side AB of this trapezoid ABCD is equal to 16 units in its length, AD equals to 17, BC equals to 25, and this is side DC equals to 44 units in its length. Again, our mission is to find out the area of this trapezoid ABCD. Actually, we know that the area of any trapezoid is equal to the sum of its two parallel bases times the height over 2. Again, the area of any trapezoid is equal to the sum of its two parallel bases times the height over 2. Therefore, the area of this trapezoid ABCD must be equal to the area of its two parallel bases. The two parallel bases are AB and DC. So the sum of the two parallel bases is AB plus DC times the height. We define the height as h divided by 2. So in total, if we found out that the area of this trapezoid ABCD is equal to AB plus DC times h over 2. So that is all. The area of trapezoid ABCD is equal to the sum of its two parallel bases. That is actually AB plus DC times the height. We define the height as h, therefore it is times h divided by 2. And the height h must create 90 degrees with the two parallel bases AB and DC. So, in order to find out the area of this trapezoid ABCD, we will do a construction. That is to say, from this point A, we will draw perpendicular on DC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and DC. This point is point E. We define the length of this line segment DE as x. And finally, we define the length of this line segment AE as h. AE, that is equals to h, is one side of the right triangle AED, but h is also the height of trapezoid ABCD. Why h is the height of trapezoid ABCD? Because of the fact that the height h creates 90 degrees with the base DC. Here, this angle equals to 90 degrees and this angle equals to 90 degrees. And therefore, h is also the height of trapezoid ABCD. So in the next step, I will copy the right triangle AED in a new page and we will implement the Pythagoras theorem on this right triangle, triangle AED. Here by PT is abbreviation for Pythagoras theorem. So actually, this is the right triangle AED that is according from the original drawing. According to the Pythagoras theorem, in this right triangle AED, AD square, that is the square of the hypotenuse, is equal to AE square plus DE square. So I write it down. This will be equation 1. AD square, that is the square of the hypotenuse, is equal to AE square plus DE square. The length of the hypotenuse AD is 17, according to what is given in the question. So AD square is 17 squared, that is 289. And it is equal to AE square. AE is 8, therefore AE square is 8 squared. Plus DE square. DE is x, therefore DE square is x squared. So in total, according to equation 1, we found out that 8 squared plus x squared equals to 289. In the next step, we will do another construction. That is to say, from this point B, we will draw perpendicular on DC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B in DC. This point is point F. We know that side AB is parallel to side DC. Therefore, those two angles, they are both located between the parallel lines AB and DC, and therefore they are defined as an interior angles. Again, those two angles are both located between the parallel lines AB and DC, and therefore they are defined as an interior angles. In addition, those two angles, they are both located on the right side of the straight line AE, and therefore they are also defined as one-sided angles. So in total, those two angles, they are defined as one-sided interior angles. And according to rule 16, the sum of two one-sided interior angles is equal to 180 degrees. So repeat quickly on rule 16. According to rule 16, the sum of one-sided interior angles is equal to 180 degrees. So in the drawing, we have here line A that is parallel to line B, and we also have here line I that cuts the two parallel lines A and B. So those two angles, that is to say angle 4 and angle 5, they are both defined as one-sided interior angles, and therefore according to rule 16, this rule 16, the sum of those two angles is equal to 180 degrees. Here you can see that angle 4 plus angle 5 is equal to 180 degrees. Likewise, those two angles, that is to say angle 3 and angle 6, they are both defined as one-sided interior angles, and therefore according to this rule 16, the sum of those two angles is equal to 180 degrees. You can see here that angle 3 plus angle 6 is equal to 180 degrees. So we can actually implement rule 16 in our drawing. While put in our drawing, so they explain to you that those two angles are both defined as one-sided interior angles, and therefore according to rule 16, the sum of those two angles is equal to 180 degrees. So actually, this is the missing angle, this is angle BAE, plus this angle that is the right angle. In total, the sum of those two angles is equal to 180 degrees. So I'll write it down. The missing angle is angle BAE plus this angle that is the right angle. In total, the sum of those two angles is equal to 180 degrees according to rule 16. So here we subtract 90 degrees from this equation, and we get that the missing angle BAE is equal to 180 degrees minus 90 degrees is 90 degrees. So if we found out that the side of this missing angle BAE is 90 degrees, according to rule 16, of course. So inside quadrangle ABFE, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrangle ABFE, we have 4 right angles. And according to rule 5, any quadrangle that has 4 right angles must be this rectangle if not a square. So we relate to this quadrangle ABFE as a rectangle because it has 4 right angles. So write it down. This is quadrangle ABEF, and it is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So an rectangle ABFE, side AB must be equal to the opposite side FE. But AB is 16, therefore FE is also 16. Likewise, according to the same rule, in the same rectangle ABFE, side AE must be equal to the opposite side FB. But AE is Z, therefore FB must be also equal to H. What is the length of this missing line segment FC? From the drawing, it is very easy to see that FC in total equals to DC minus DE minus EF. Again, FC in total equals to DC minus DE minus FE. So it is known FC is equal to DC minus DE minus EF. So FC in total is equal to DC, that is 44, minus DE, that is X, minus FE, that is 16. So in total we found out that FC equals to 44 minus 16 is 28 minus X. So FC equals to 28 minus X units in its length. FC equals to 28 minus X. In the next step, I'll copy the right triangle BFC in the new page, and we recommend the Pythagoras theorem with this right triangle BFC. Here by PT is evolution for Pandola's theorem. So actually, this is the right triangle BFC that I call it from the original drawing. According to the Pythagoras theorem, in this right triangle BFC, BC squared, that is the square they produce, is equal to BF squared plus FC squared. So I write it down. So BC squared, this will be equation 2, BC squared is equal to BF squared plus FC squared. The hypotenuse BC is 25, therefore BC squared is 25 squared, that is 625. And it is equal to BF squared. BF is 8, therefore BF squared is 8 squared. Plus FC squared. FC is 28 minus x, therefore FC squared is 28 minus x squared. So in total we found out that according to equation 2, 625 equals to 8 squared plus 28 minus x squared. Here we'll open the brackets on this side of the equation. And we get that according to this equation, equation 2, 625 is equal to 8 squared plus 28 minus x squared. 28 minus x squared equals to 28 squared, that is 874 plus x squared minus 2 times 28 times x, that is minus 56x. So total actually according to equation 2, this equation 2, we found out that 625 equals to 8 squared plus 874 plus x squared minus 56x. So here we subtract 625 from this equation 2. So in this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have 8 squared plus x squared minus 56x, and 874 minus 625 is 159. So in total we found out that according to this equation 2, 0 equals to 8 squared plus x squared minus 56x plus 159. Actually, according to equation 1, we already found out that 8 squared plus x squared equals to 289. So you can substitute 8 squared plus x squared in this equation 2 by 289. We do it now and we get that according to equation 2, 0 equals to 289, 8 squared plus x squared is 289, according to equation 1, minus 56x plus 159. So here we will add 56x to this equation 2, and we get here that 0 plus 56x is 56x, and it is equal to 489 plus 159. 489 plus 159 is equal to 448. So in total we found out that according to equation 2, 56x equals to 448. Here we divide this equation 2 by 56, and so you get that according to this equation 2, x equals to 448 over 56 is 8. So x equals to 8 units in its length. Return back to equation 1. According to equation 1, we found out that x squared plus x squared is equal to 289. We just right now found out that x equals to 8. if x equals to 8, it means that x squared equals to 8 squared, that is 64. Therefore, we can substitute x squared in this equation 1 by 64. We do it now and we get that 8 squared plus x squared, that is 64, is equal to 289. Here we subtract 64 from this equation, equation 1, and finally get that 8 squared equals to 289 minus 64 is 225. So in total, we should find out that according to this equation 1, 8 squared equals to 224. Here we take a root of this equation, and finally get that according to this equation 1, h equals to the square root of 225. The square root of 225 is 15. So in total, we should find out that h equals to 15 units in its length. That is to say, the height of this trapezoid ABCD is equal to h is equal to 15 units. So the height of trapezoid ABCD is 15 units. Our mission is to find out the area of this trapezoid ABCD. We have already found out that the area of trapezoid ABCD is equals to the sum of its two parallel bases, that is actually AB plus DC times the height that is h times the height that is h over 2. AB is 16 plus DC is 44. We just right now found out that the height h is 15 divided by 2. So in total, the area of trapezoid ABCD equals to 16 plus 44 is 60 times 15 over 2. 60 over 2 is 30, so in total this expression equals to 30 times 15. 30 times 15 is 450. In conclusion, we found out that the area of trapezoid ABCD, that is the area that we are looking for in this question, the area of trapezoid ABCD is equal to 450 square units. Okay, again, we found out that the area of this trapezoid ABCD is equal to 450 square units. So we finished with the second question. In the next step, I'll summarize the lecture. I will start with the first question, of course. Our mission in the first question is to find out the area of this circle. It is given as the question that we have here the common standpoint point P. From this common standpoint point P, we have two tangents to this circle, tangent PE and tangent PB. In addition, we have the right triangle ACP, and this is side CP of the right triangle ACP, that equals to 4 units in its length. The right triangle ACP cuts the circle at 2 points, point A and this point. In addition, we know that the line segment BC is equal to 1 unit in its length. Again, our mission is to find out the area of this circle. So first of all, we implemented rule 2 in our drawing. Here we have the common standpoint point P. From this common standpoint point P, we have two tangents to the circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB according to rule 2. So I put again according to rule 2, PA equals to PB. But it is given as a question that PB equals to 4 plus 1, that is 5. So we can write here that PB equals to 5. And from this equation, PA equals to PB equals to 5. We derive that PA is also equals to 5 units in its length. So this is my cement PA, that is equals to 5 units in its length. In the next step, we define the center of this circle. This point is point O. We also define the radius of this circle as x. In the next step, we join points O and B together by a straight line. What is the definition of line segment OB? Line segment OB is the radius of this circle, because it starts from the center and ends at point B, that is a point on the circle itself. So OB is the radius of this circle, that is equal to x according to our definition. Here we can implement rule 1. Why? Because we have the radius of B that is 1 to point B, that is the point of tendency PB. With this circle, whenever your radius is 1 to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees, according to rule 1. It is given as the question that PB is a tangent. PB is a tangent, it is absolutely a straight line. So if we focus on the upper side of the straight line PB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of PB at point C? We have this angle that is right angle plus this missing angle, in total the sum of those two angles must be equal to 180 degrees. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we did a construction. That is to say, from this point O, we draw perpendicular on AC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees. Repeat again. In the next step, we do a construction, that is to say from this point O, we draw perpendicular on AC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AE, this point is point E. By doing this construction, quadrilateral OECB. Inside the quadrilateral OECB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this missing angle, in total must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside the quadrilateral OECB, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be its rectangle if not a square. So we relate to quadrilateral OECB as rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle OECB, side BC must be equal to the opposite side OE. But CB is 1, therefore OE must be also equal to 1. Likewise, according to the symbol in the same rectangle OECB, side OB must be equal to the opposite side EC, but OB is x, therefore EC must be also equal to x. What is the length of the missing 9797 AE? AE equals to AC minus EC. Again, AE equals to AC minus EC. So AE equals to AC, that is 3, minus EC, that is x. So in total, AE equals to 3 minus x units in its length. We join points O and A together by a straight line. OA is of course the radius of this circle, that is equals to x according to our definition. In the next step, I copy the right triangle OAE in a new page, and we implemented the Pythagoras theorem on this right triangle OAE. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse is equal to the sum of the squares of the perpendiculars. So the hypotenuse in this right triangle OAE is equals to x, therefore OA square is x squared, and it is equals to AE square. A is 3 minus x, therefore AE square is 3 minus x squared, plus OE square. OE is 1, therefore OE square is 1 square. So in total, we found out that x squared equals to 3 minus x squared plus 1. Here we open the brackets on this side of the equation, and finally found out that x squared equals to 3 minus x squared. 3 minus x squared equals to 3 squared, that is 9, plus x squared, minus 2 times 3 times x, that is minus 6x, plus 1. So here we have x squared on both sides of the equation, so x squared will get cancelled. After we cancelled x squared, in this side of the equation we have nothing, that is 0. On the other side of the equation we have 9 plus 1, that is 10, minus 6x. In total, we should found out that 0 equals to 10 minus 6x. Here we added 6x to this equation, and finally found out that 6x equals to 10. Here we divided this equation by 2, and finally found out that 6x over 2 is 3x, and it equals to 10 over 2, that is 5. So 3x equals to 5. Here we divided this equation by 5, and finally found out that x equals to 5 over 3 units in its length. So we found out that the radius x of this circle is equal to 5 over 3 units in its length. Our mission is to find out the area of this circle. Actually, the area of any circle equals to pi times the radius of the circle squared. Again, the area of any circle equals to pi times the radius of the circle squared. Therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is x, so the radius squared is x squared. So in total, the area of this circle is equal to pi x squared. X is 5 over 3, therefore x squared is 5 over 3 squared. So in total, the area of this circle is equal to pi times 5 over 3 squared. So it is pi, and 5 over 3 squared is 5 squared, that is 25, over 3 squared, that is 9. So in total, we should find out that the area of this circle is equal to either 25 pi over 9 square units, or in terms of numbers, the area of the second is equal to 8.727 square meters. So we finish with the first question. In the next step, I presented to you the second question and we solved it. Our mission in the second question is to find out the area of this trapezoid ABCD. It is given as a question that AB equals to 16, AD equals to 17, BC equals to 25, and side DC of this trapezoid ABCD is equal to 44 units in its length. Again, our mission is to find out the area of this trapezoid ABCD. Actually, the area of any trapezoid is equal to the sum of its two parallel bases times the height over 2. And therefore, the area of this trapezoid ABCD must be equal to AB plus DC, that is the sum of its two parallel bases, times the height, that is h over 2. Okay, again, the area of this trapezoid ABCD is equal to the sum of its two parallel bases, that is actually AB plus DC, times the height h over 2. The height h must create 90 degrees with the two parallel bases AB and DC. So in order to find out the area of this trapezoid ABCD, we did a construction. That is to say, from this point A, we go perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the tangent point of the perpendicular from point A and DC. This point is point E. We define the length of this line segment DE is x, and the length of AE is h. H is also the height of trapezoid ABCD. Why h is the height? Because it creates 90 degrees with the base DC. In the next step, I'll copy the right triangle AED in the new page and implemented the Pythagoras theorem with this right triangle AED. This is the right triangle AED. This is a copy from the original drawing. According to the Pythagoras theorem, with this right triangle AED, AD square equals to AE square plus DE square. Again, AD square equals to AE square plus DE square. AD is 17, therefore AD square is 17 square, that is 289, and it is equal to AE square. AE is h, therefore E square is h square, plus DE square. DE is x, therefore DE square is x square. So in total, actually, according to equation 1, we found out that h square plus x square equals to 289. In the next step, we did another construction. That is to say, from this point B, we go perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the tangent point of the perpendicular from point B in DC. This point is point F. So we know that AB is parallel to DC. So actually, those two angles, they are both located between the parallel lines AB and DC, and therefore they are defined as an interior angles. But those two angles, they are also located on the right side of the straight line AE, and therefore they are also defined as one-sided angles. So in total, those two angles, they are both defined as one-sided interior angles. And according to rule 16, the sum of two one-sided interior angles is equal to 180 degrees. This is to say, the sum of those two angles that are defined as one-sided interior angles is equal to 180 degrees. So this is the missing angle BAE plus this angle that is a right angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 16. I repeat again. The missing angle BAE plus the right angle, in total, must be equal to 180 degrees according to rule 16. Here we subtracted 90 degrees from this equation and finally found out that the missing angle BAE is equal to 90 degrees in its size. Okay. This is the missing angle BAE, this is a right angle. So okay, inside quadrangle ABFE, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 missing angle, in total it must be equal to 360 degrees. according to the rule that said that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral ABFE we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this right angle plus a square. So when we go to quadrilateral ABFE, it's a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in a rectangle ABFE, side AB must be equal to the opposite side FE. But AB is 16, therefore FE must be also equal to 16 in its square. Likewise, according to the same rule, in the same rectangle ABFE, side AE must be equal to the opposite side FB. But AE is Z, therefore FB must be also equal to H. What is the length of the missing line segment FC? FC equals to DC minus DE minus CF. Again, FC in total equals to DC minus DE minus CF. So FC equals to DC that is 44 minus DE that is X minus FE that is 16. So in total FC equals to 44 minus 16 that is 28 minus X. So FC equals to 28 minus 16 it's in the in the next step, by going the right triangle BFC in an equation, we implemented the Pythagoras theorem in this triangle BFC. Actually, this is the right triangle BFC, then I come from the original drawing, according to the Pythagoras theorem. In this right triangle BFC, BC squared, that is the square of the hypotenuse, is equal to BF squared plus FC squared. BC is 25, therefore BC squared is 25 squared, that is 625, and it is equal to BF squared. BF is Z, therefore BF squared is Z squared, plus FC squared. FC is 28 minus X, therefore C squared is 28 minus X squared. So in total, according to equation 2, we shall find out that 625 equals to H squared plus 28 minus X squared. Here we open the brackets on this side of this equation and equation 2, we shall find out that according to this equation and equation 2, 625 equals to H squared plus 28 minus X squared. 28 minus X squared equals to 28 squared, that is 874, plus X squared minus 2 times 28 minus X, that is minus 56X. So in total, according to equation 2, we actually found out that 625 equals to H squared plus 134 plus 874 plus X squared minus 56X. Here we subtract 625 from this equation, equation 2, and found out that this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have X squared plus X squared minus 56X, and 874 minus 625 is equal to 159. So according to equation 2, in total found out actually that 0 equals to H squared plus X squared minus 56X plus 159. According to equation 1, H squared plus X squared equals to 289. Therefore we can substitute H squared plus X squared in this equation 2 by 289. We did it, and we found out that 0 equals to H squared plus X squared is 289 minus 56X plus 159. Here we added 56X to this equation, and finally found out that 56X equals to 289 plus 159 equals to 448. So in total, actually, according to equation 2, we found out that 56X equals to 448. Here we divided this equation 2 by 56X. We finally found out that according to this equation 2, X equals to 448 over 56. So 448 over 56 is 8. So we found out that X equals to 8 in its name. Then I return back to the equation 1. According to equation 1, we have already found out that H squared plus X squared equals to 289. And we just found out that X equals to 8. If X equals to 8, it means that X squared equals to H squared, that is 64. Therefore, we can substitute X squared in this equation 1 by 64. We did it, and we found out that H squared plus X squared, that is 64, equals to 289. Here we subtracted 64 from this equation 1, and we found out that H squared equals to 289 on 64 is 225. So H squared equals to 225. Here we took a root out of this equation 1, and finally found out that H equals to the square root of 225. The square root of 225 is 15, so H equals to 15. We found out that the height of this trapezoid ABCD is equal to 15 units. Our mission is to find out the area of this trapezoid ABCD. I already explained to you that the area of this trapezoid ABCD is equal to the sum of its two parallel bases, that is AB plus DC, times the height, that is h over 2. Repeat again. We already found out that the area of trapezoid ABCD is equal to the sum of its two parallel bases, that is AB plus DC, times the height, that is h over 2. AB is 16, DC is 44, times the height edge is 15, divided by 2. 16 plus 44 is 60, so in total this expression equals to 60 times 15 over 2. 60 over 2 is 30, so in total this expression equals to 30 times 15. 30 times 15 is 450. So in total, we found out the area of this trapezoid ABCD is equal to 450 square meters. Okay, thank you very much.